All right, we have started recording. So 1A only. I'll give you a minute on that. And while you're working on that, I would love a little bit of feedback. I've never done a system where all my notes are so easily accessible to students. So in theory, you don't have to take notes as a student. I'm wondering if I myself was a student, whether I'd be taking notes in this class, because sometimes that helps me to stay engaged as I'm taking notes. I'd wonder if I'd find it all that helpful. What are you all experiencing? Is it helpful to have these notes, or it's not a big deal, or if you could just go into the chat channel and just tell me what's your experience with the notes, if it's the OneNote thing. That'd be useful information for me in the future. Because, when we go back to live classes at some point, I may decide to do something like this if it's really helpful to students, if they're using it a lot. If not, then maybe not. Give just a little bit more time. Okay. All right, anybody need more time on 1A? Then let's go through it. We need a function f and a function g that are the same degree. And the ratio, like this, could be 8x to the 7th minus 2x. This could be, it has to be, the ratio of the coefficients has to be 4, has to be the same degree, plus 5x cubed, doesn't matter, minus 4. Something like this. That's an example of a function that would satisfy this condition. The horizontal asymptote of the quotient is 4. All right, go ahead and do B. Hold it. B is exactly the same thing. Let me change B. Let me look on my notes. I must have copied that and then not made the change. Oh yeah, the next one is supposed to be 0. Okay. So do part B. All right, so one of the questions with the OneNotes is how do you access? How do you find them? Can anybody answer that for Alondra and for anybody else who's wondering? I forgot where I placed them so that you could all get to the OneNotes.
The way I use it is through the announcement you made through Canvas.
Okay, and then there's a link right there, right? And then you
Yeah,
just put that into your browser, and then from then on you have the notes. Okay,
yeah.
great. And is this, who am I talking to? Is that
It's Sally.
Sally? Okay, thanks, Sally. Okay. All right. Anybody need more time on B? All right. Let's. Thus, I need a function g of x that has greater degree than that one. So like 3x to the 8th, while this one is whatever, 7x to the 3rd minus 2x plus 3. All right. As long as the degree of the denominator is higher, you've got this one. And then part C, let me give you a moment with that. All right. Anybody need more time with C? Um, so it does not exist. The f has to have the higher degree. So 5x to the 5th minus 2x, 3x squared minus 4, something like this. As long as the first one has a higher degree. All right, and you might wonder, could we have done something not polynomials? Could I have done f of x equals e to the x? Sure. And then, since that's a really fast-growing function, it'll grow faster than any polynomial function eventually. But we typically, when we have fractions, a function over a function, our preferred functions are polynomials, simple polynomials, and then we look at the asymptotes and all that stuff of those. All right, so let's go to number 2. Well, let me have you give me a little feedback on number 1. So just let me know if you're good to go on 1.
Question.
You understood everything there. Yes, question.
I have a quick question. So for number 1A,
Uh-huh.
it's as long as the degree of the denominator is lower than the numerator. Is that correct?
For A, no, they have to be the same degree. That's the only
Oh, the same
time
degree.
you can get a non-zero horizontal asymptote.
Okay, and for C,
Mm-hmm.
what is the rule again?
The numerator has to have greater degree
Thank you, sir.
than the denominator, and then the function, the horizontal asymptote does not exist. All right, let me just check in on the feedback. All right. Thanks for your honesty with the feedback, and I can address that at some point. And all right, let's go to number 2. Part A. So here's the function f, and here's 2 points. A, f of a, x, you come across the f of x. Write an expression for the slope of the secant line between these 2 points. So let me give you a minute for that. And Gerardo and Daniela, if you're available to stay after class a little bit, we can work on that immediately after class today. Okay, anybody need more time? Number 2? And let's go ahead and look at it. So I am going to rewrite this as a point, a f of a. Get it in real familiar terms. X, f of x is this point. And then this line is the secant line, and it has slope, difference in the y's, over the difference in the x's. So that's really, the top is the change in the y, and the denominator is the change in the x. Change in y over change in x for the slope. Alright, so that's the expression for the secant line between those 2 points. Write an expression, this is B, write an expression for the exact slope of the tangent line at x equal a. So this time, the tangent line at x equals a is this. And you're going to write expression for, and it'll give you the exact slope of that tangent line. Anybody need more time with this one?
Just a couple more seconds.
You bet.
Thank you.
Mm-hmm.
All right, I'm good to go.
All right. So what we're going to do, let me shrink this. We're going to get the same thing that we had over here, but we're going to do it with the limit. And we're going to take the x and bring it towards the a. For instance, if we brought the x, let me go to blue here. If we brought the x to the halfway point, and then we got here, then the line between here and here, you see, is a better approximation of the slope of the green line. If we could bring it even closer, then we'd get to here, and we'd get an even better approximation of the slope of the green line. So we're going to take the limit as x approaches a of the same expression. Now, this limit is, remember what a limit was, you can think of it as a sequence of a whole bunch of numbers, like 4.9, 4.99, 4.9999. That's getting ever closer to a result, maybe 5. And then, so this limit value does give you the exact slope if you can look at that as a total limit of there. All right, so give me feedback on this too. Might be kind of abstract what we were doing, but give me some sort of feedback in the text channel for number 2 so far. Okay, let's come back now. So, the symbol for this exact slope at A, this is introducing this new section. And what we're going to use is the exact slope at a point. Instead of F at A, we're going to call it F prime at A. Looks like an apostrophe right after the F. Okay, and the name for this, the exact slope at a point, so it's the slope of a tangent line. The name is called the derivative. And this is the fundamental concept in all of calculus. And if you take calculus 1, 2, and 3, we will spend a great deal of time on the derivative and then the inverse of the derivative, which we'll eventually call the integral. And that's basically what Calc 1 and 2 and 3 are all about, is the derivative and the integral. And we take it in all kinds of different contexts. But this is the heart and soul of what calculus is about, is this function and its inverse, which will be called the integral. Okay. When we have the derivative, there are 2 possible definitions of the derivative. And this is definition 1, page 133. So if we go to the textbook, and if I go to page 133, it's telling you the average rate of change between 2 points. So it's very much like the pictures we just gave. So there's A and there's X, A and X, and we're trying to find the slope of this red line. Now their curve is curved a little differently than my curve. But notice, when you take between these 2 points, A and X, you get the slope of this green line, and that's the slope of the secant line. And then you get the slope of the red line if you take the limit as you take the X and you push it back further towards A. Now the picture is a little deceptive in that the X doesn't have to be to the right of A. The X could be to the left of A, and then we'd approach the A from this direction, because there's no plus or minus with this limit over here. But this is, again, as we move this point closer and closer, we get better and better, the slopes become better and better estimates of the slope of this red line, which is the line that we're really after. And then, so that's the slope of the tangent line, m subtangent, and then that's going to get the name derivative. Okay. Now, let's go and look at it in a different manner. So, practice quiz, problem number 3. We have A, f of a for this point, a plus h, f of a plus h. The same two questions. Write an expression for the slope of the secant line. So a couple of you put down, need a little more practice. Well, here's a little bit more practice. See if you can get it in this context. I've changed it slightly. And then write an expression for the exact slope of the tangent line at x equal a. Okay, so do both a and b on number 3. All right, does anybody need more time? All right, let's look at it. Expression for the slope of the secant line. So this is a f of a plus h, f of a plus h, and the slope, the secant line between these 2 points is difference in the y's over the difference in the x. Now when you take the difference in the x's, it's a plus h minus a, and the a's cancel out, and all you're left with is h. It doesn't look like it's a change in y over a change in x, but it is. That's what we're getting. The top looks like a change in y, the bottom doesn't, but the way we set that up, a and a plus h, makes the bottom really simplify down to h. Now in this picture you can see that the gap between here and here is h. So when I need to write expression for the exact slope, I'm going to take this thing and I'm going to get, now the textbook puts it as m of the tangent line, slope of the tangent line is equal to, it's going to be the same thing but with the limit. But this time it's not x approaching a. Up here it was as x approached a, as this point moves towards the first point. How do I get the second point to move towards the first point? I have to take what goes to what. Anybody have any idea?
As h goes to 0?
As h goes to 0. As that gap between them, so if you made h half as small, you'd be here. Quarter as small, you'd be here, and you'd move it slower, more and more towards it. So then we get f A plus H minus F. A all over H. So, we're going to eventually prefer this second format because it's so convenient with this H being the gap between. But we often start out with them being like A and X, like this. But we have two different formats. And let me zoom in again. Alright. So, the name of this is this is the exact slope. It's once again the derivative. And this is definition 2, page 135. And so alternate definition. And you see it's same kind of thing. And if we go to the page right before that, it shows the picture. A plus H, the gap between them, they show the H right here. As H goes to 0, brings the second point closer and closer to the first, and the slopes of the green lines become better and better estimates of the slope of the red line. And the limit of those slopes is exactly the slope of the red line, right there.
I have a question.
Yes.
This looks like the difference quotient that we were doing earlier.
Yes.
So is that similar to what we're doing now?
That is exactly the difference quotient. When we were doing the difference quotient, the whole objective of that was to get you used to the algebra involved, because it's kind of tricky algebra to simplify those things down, because we're going to be working with that difference quotient. But when you put the difference quotient behind the word limit, it turns into the derivative. It's the central concept of calculus. And hopefully, since we practiced with the algebra, when we do these problems, you won't get too, your brain power won't get all used up by just handling the algebra. You'll be able to also reserve some brain power to see, this is representing the slopes as well. And when I first learned calculus, this was the most challenging part for me, was there were all these computations that I had to get good at, and then there was also, what does it represent? And so I had to keep both things in my head kind of simultaneously, kind of like, how can I do both of these? And I found that at the beginning I could only rotate between the one point of view and the other point of view. And sometimes I would get stuck in one point of view. I could just do the computations and I couldn't figure out what it all meant. And I'd have to do this really big, extensive review. And then start to kind of integrate, this is the way I compute it, and this is what it means as well. Alright. So, those are the two different definitions. Alright, and let's go to any other comments before we move away from that? Comments, questions? That's kind of introducing the section for today, which is the derivative. It's a pretty big deal.
I wanted some clarification about it. Does the derivative apply to a function strictly if it's continuous over an interval? So for example, like say we're approaching something, but then at that point, if there's like like we talked about, like the removable discontinuities, would it not apply to those types of functions where you have a discontinuity?
Okay, good question. It turns out that if it's a whole discontinuity, then yes, you can have a derivative at the point where the hole is, because it's going to be this definition, the slope of the tangent line as h approaches 0, and h is never allowed to get to 0. So a whole discontinuity will be okay, and you'll still have a derivative at that point. But if you have a jump discontinuity, you're moving along, all of a sudden you jump up to a different level. Then, at that place where you jump, there will be no derivative, because the limit from the left, as h approaches 0 from the left side, will give you a different slope as you get from when you go from the right. So, very good question. We're going to need not total continuity, but we can deal with holes, but we can't deal with jumps and still have a derivative. It'll not have a derivative just at that one point where the jump is happening. Any other questions, comments?
So then if you have a graph that has a discontinuity at x, and then they have another point above it where f of 1 is a number, and then f of 2 is a number plus that 1, does that mean that that's a discontinuity as well, which means that we can't take the derivative of that either?
From what you're describing, suppose the discontinuity is over here at 4. My function is going along to here. What's going to happen at 4? Kylie, am I going to be jumping up, or am I going to just be doing a hole, or what?
It would be a hole.
Okay, so let's make a hole. And so then it gets filled in here. And then afterwards, would I stay along this curve, or would I jump up to this one?
Well, sometimes the line would continue.
Like this?
Yeah.
Okay. That, the derivative will exist even when x is equal to 4. Because
Oh, okay.
the limit from the left and the limit from the right will be the same. And the tangent line here will be here. The tangent line here will be here. And you notice they're the same. You're going to get the same slope from either direction. And you're not allowed to get to 4. So it's okay. Okay. The limit isn't allowed to get to its destination. All right. Let's go to questions on the homework. Somebody had typed in, what was it, number 12?
Yeah, number 12.
And I believe that was on 2.6. And that's page 113. So let me go here. Actually, page 112. Okay, determine the points on the interval 0 to 5 in which the following function f has discontinuities. At each point of discontinuity, state the conditions in the continuity checklist that are violated. All right, so now notice it says determine the points in the interval 0 to 5, but it doesn't include the point 0. That's called an open interval. If it included the point 0, it would have a bracket 0 to 5. And then we'd have to say what happens at 0, whether it's discontinuous or not. So we start by looking at 1. At 1, it is discontinuous, because we'd have to lift our pencil when we were drawing it. Which one of those does it violate? The continuity of functions, if we look back at the 3 things, f of c has to exist. F of c does exist. There was a dot right above that point. The limit has to exist, both sides of the thing, and they have to be equal. The first 2 parts. So if we go back to here, f of c exists. The limit does exist, because when you approach 1 from the left and from the right, you both get a height of 3, but they don't, it does not satisfy part 3. The 3 and the 4 are the answers for part 1 and 2, and they are not equal to each other. And then at x equals 2, there's also a discontinuity, and here f of c exists. F of c is 2. The left-hand limit, though, is 2, while the right-hand limit is 3, so part 2, that doesn't exist. That limit does not exist. And they can't be equal to each other since one of them doesn't exist. Number 3, or at x equal 3, f of c does not exist. So a is violated. B, the limit from the left and from the right is both 4. That's okay. C, they can't equal each other because the first one, f of 3, does not exist. And then that's it. All right. Does that answer your question for number 6?
It was supposed to be number 12, I think, for what
no.
Dominic was asking. It's using the graph 5, number 5, but it's asking for what points are continuous and how does it, what does it continue on the left or right?
Yeah, for number 12, we're using graph 6, right?
Oh, okay. Exercising, so we're doing the right graph. Determine the intervals of continuity for the following. At which endpoints of these intervals of continuity is f continuous from the left or continuous from the right? Okay. So let's go back to here. Intervals of continuity. Are from 0 to 1, and at 1 it's not continuous. And then from 1 to 2,
Are you using graphs number 6 or graph number 5?
I think I'm using graph 6.
Okay.
So from 0 to 1
Thank
along
you.
the x-axis, 1 to 2 along the x-axis, from 2 to 3.
Shouldn't the 2 have a bracket on the right of it? The 1, 2?
All right. Intervals of continuity. Now that's, let's go back to the question. At which endpoint is continuous from the left or continuous from the right? All right, so the textbook talks a little bit about that, continuous from the left and from the right, and if it's continuous, I contains its endpoints, continuity, I mean continuous from the left or from the right. Okay, yes, that's exactly how they're referring to that. So let's go back to that. So this one right here, that should be a bracket with the 2. And then we'll come back to union. So we went 2 to 3 and then 3 to 5. There's all the continuous. And this one right here, we call it continuous from the left because you can go all the way up and include that endpoint. All right. Any other questions?
Do they want us to say specifically like left continuous at point 2? Is that...
At which of these intervals of continuity is continuous from the left? You know what? I think just by putting the bracket, that's clear enough. That's all you need. Anything else? All right, that's our smallest.
Quick question.
Yes.
Are you going to be using this on the test, this type of question, just because it's just a little bit difficult for me? So I need to study on it a little bit more.
It's possible.
Okay.
Yeah. If you're getting confused on this, you might be making it more complex than it is. It's just saying where along the x-axis do you not have to lift your pencil. You don't have to lift your pencil from 0 to 1 and then from 1 to 2, but at 1 you had to lift your pencil, so you couldn't include that in there. And then, you know, if it was a filled in circle, you used a bracket. That's it.
Thank you.
You're welcome.
So we had other questions on the homework.
Oh, could you tell me what they are?
Gerardo asked for, oh, let's do
Okay.
2.5, sorry. Let's do number 74.
74 and 2.5. Let's go look at that. All right, so that's page 101. Okay, and then it says to analyze the horizontal asymptotes, and then find the vertical asymptotes. So horizontal and vertical asymptotes, and let's, we got this. All right, now, my first instinct when I look at one of these is that the only way you're going to get horizontal or vertical asymptotes is if you have a fractional function. And this one doesn't have a fraction in it, so it's not going to have any horizontal or vertical asymptotes. It's my first instinct on it. But there's something I need to look at with this square root over here. All right. Now this is a little bit complex in the thought, but if you get it, it becomes very, very simple. But just look at this for a moment. Let's go into the draw. If you look at this right, you see that this thing that I'm circling and this thing that I'm circling are almost the same thing. Imagine that this plus 1 wasn't here. Then the square root of 16x to the fourth would be exactly 4x squared. So when x is really, really big, like 100 million, these two things are almost exactly the same. This one was just the tiniest bit bigger before you square rooted it, and then the difference is going to be really, really, really close to 0 when you take this. And then, so you're getting something really close to x squared times something really close to 0. Now, this is not going to have any vertical asymptotes, because to have vertical asymptotes, you have to have a fraction. You got to have, something. Now, The horizontal asymptotes, though, as x goes to infinity, this goes to infinity, while this goes to 0. Now, hold it. I didn't do that right. Let me go with a different color. As x goes to infinity, this goes to infinity. All of this goes to 0, because those two will be nearly equal to each other in your life. Now, when some x is going to infinity, what are these two things doing? They could, if one's going to infinity and the other's going to 0, it all depends on which is going there faster. Let me kind of show you, for instance. Limit as x goes to infinity of x to the third over x. As x goes to infinity, the numerator goes off to infinity, the denominator goes off to infinity. But the numerator is going off to infinity faster than the denominator is going off to infinity. Although they're both going off to infinity, whichever is going there faster is going to dominate the total fraction. If you had it in reverse, x to the second over x to the fifth, the higher power in the denominator, then this is going off to infinity. This is going off to infinity. But the whole thing is going to 0 because the denominator is going off to infinity faster than the numerator is. It depends on which is going to its destination at a quicker rate. And the same thing is going to be the case over here. When these two things multiplying together, the result could be, for instance, let me take you a limit. As x goes to infinity. It's the same as this kind of stuff, but just rewriting it separately. 1 over x times x to the third. This one is going to 0. This one is going to infinity. But which one is the whole thing going to go towards? Well, going to go towards infinity, because the one that's going towards infinity is going there faster than the one that's going towards 0 is going towards. Everybody following? It's kind of, it's a pretty depthful way of looking at it, but we got to see which one is going to its destination faster. Now, this is not the kind of problem that you're going to see on a test. It's a pretty advanced way of looking at something like this, but to be able to say which one's going faster to its limit, I might have to get into looking at, so f of x is equal to x squared times I might use this trick of multiplying top and bottom by the conjugate. We learned that before, because that will get rid of all the square roots. And sometimes this is a dead end, but sometimes it really reveals something to us. So, so this is equal to, when I multiply out in the top, I get x squared. When I multiply these two things, I'm going to get 16x to the fourth. the two middle terms will cancel each other out. The last term will be this square root times this square root, and the square roots will disappear. And what happens up above is these cancel out, and I get equal to, this becomes a negative 1, okay. Now, I still have to look at the limit as x goes to infinity of this expression. So now the limit of all of this, now this right here, as x gets really, really, really large, this is going to get closer and closer to that 1 won't make much of a difference. It'll become really close to 4x squared. And so this will become 8x squared as x gets really, really, really large. That 1 becomes less and less significant. And so then these x squareds will cancel out, and you'll get negative 1/8. So it's a very advanced problem, but this thing will get infinitely close to negative 1/8. And if you don't believe me, take a really, really large number, like, 1,000,000, plug it in for x squared, and you'll get really, really close to negative 1/8. All right, let's look at another one. 2.6, number 28. Now, by the way, when you come up to those really difficult ones, you're going to have some really challenging problems, and they're put there intentionally. And that's the great thing about a college math class, is we put a variety of problems out there to appeal to lots of different, people and wherever they're at. And we put some really challenging ones, and you can get a tremendous amount out of this course if you really push yourself towards those. But change your expectations. You won't, generally, you don't get these the first crack at them. You try it and you say, whoa, I have no idea. And then you come back an hour or two later and you make a little bit of headway, and then you come back a little later and you get another idea, and you try a few different things, and you go down a few dead ends and so on, but eventually you can get them.
Professor, so I'm sorry, just to make sure I understand. So for 74, then the horizontal asymptote should have been at negative 1/8?
Yes.
Okay. And then, but the limit of the function as it's approaching infinity, that was 0 or also negative 1/8?
As it approaches negative infinity?
As it approaches either positive or negative infinity.
Notice all the powers are even.
Okay.
So it doesn't matter whether it's approaching positive or negative infinity, we're going to get the same result in the end. Yeah, and there's no vertical asymptotes for it.
Yeah, and which was, so the approaching both positive and negative infinity, that's also approaching negative 1/8, or is 0?
Correct. As x approaches either positive or negative infinity, the horizontal asymptote is negative 1/8. All right, and then 2.6, number 28. That's page 113. Determine the intervals where this is continuous. All right, so on number 28, first thing I'm going to have to do here is factor out and these are going to cancel. All right, so where is the discontinuity? Discontinuous at, well, first of all, at x equal -1, because that's a vertical asymptote. But it's also discontinuous at x equals +1. Now, there's a discontinuity there because that would cause both the numerator and denominator to be 0. 0 divided by 0 is not allowed. It's not a vertical asymptote though. It's just what's called a hole discontinuity. When it cancels out top and bottom, there's just a little hole that it leaves in the graph. But it's still a place where you have to lift your pencil to keep drawing it. So it's a discontinuity there and there. So in the intervals where it is continuous are from -∞ to -1, union -1 to 1, union 1 to infinity. That's the answer where it's continuous. All right, is that it for questions? We are at time for a break, so let's start again. At 12:44. See you in a little bit. All right, we're going to start up again, and we'll go into section 3.1, introducing the derivative. Before jumping into that, though, reminder that the exam is Thursday this week, and due on Thursday is the homework up until 3.1. Once again, there's no take-home portion or anything like that. That only happens with the first exam, and then I give you a little support at the final exam. And on Thursday, we're not going to be doing anything in class other than during that 2-hour window is when you take exam number 2. As you prepare for the exam, y'all have experience preparing for lots of different math exams. What I tended to do was I would just go through each section, and every time the directions changed, I'd make sure I do at least one problem with each of the different sets of directions, so that I was really familiar with, you know, all the kinds of things I'd be asked. And if you do that, you're really prepared well. I mean, now and then I put a problem that's not real similar, that's just a bit more conceptual. But for the vast majority of the exam, if you can do all the different types of homework problems, you're all set. You know how to do the exam. I take the problems, make them very similar to the types of problems that you've been working on. Any questions with regard to the exam or what's coming up? All right, let's go to 3.1, introducing the derivative. All right, and we start with number 1 here. The derivative, and the symbol for the derivative is f prime of a. Now, when Newton first came up with the derivative, he had to come up with a different symbol. It had to do with the function f. He used this symbol here, and he called it like a hat, f hat of a. And but in time, it became the apostrophe that we're in. So this is the more common symbol, the derivative. And what does the derivative mean? Well, it's complex. This is how you get it. It's the limit. Now remember, this is the top is the change in y. The bottom is the change in the x. So this is how we get it. And if I scroll up, I can show you the picture. It's the slope of this line right here, the tangent line. And you start by saying this, the slope of the blue line is a reasonable estimate of the slope of the green line. And then you make this h smaller, and you move the point back. Maybe you're over here now. So then when you connect these two, you get a better estimate. You keep moving that point back and getting better and better estimates. You keep track of all your results. That's a sequence, and the limit of the sequence is the slope of the green line. And so that's its definition. This is a change in y, change in x. It's a slope, but it's the limit as h approaches 0 of all those slopes. Then it represents the slope of the tangent line at x equal a. And what does the slope of a tangent line mean? That's the same as the instantaneous rate of change of f at a. So 2 and 3 have to do with the interpretation of it. Number 1 is how we get it. And you got to be able to kind of hold both in your mind at the same time. It makes me remember um, when I talked with my brother. My brother, he died of a stroke about 8 years ago. But I remember at times we would talk about our childhood. And my father was very difficult to grow up with. There were times that he was magnificent. For instance, when he talked about that, because he got out of high school and immediately went into the army. And then when he got out of the army, he got married, started having kids, had 7 kids, and he couldn't provide. He couldn't earn enough money to provide for all the kids in his family. So he did whatever it took. And so if it took him working 2 jobs, he worked 2 jobs. And he eventually got a job at Ford Tractor in management, but you had to have a degree or be getting a degree. So, and he didn't have a degree, so for 20 years he went to night school. And so he did whatever it took to provide for his family. So in that way he was a hero. And in other ways he was really difficult to live with. It was his way or no way. And not at all understanding with children, and his favorite saying was, little kids are to be seen and not heard. And so talking with my brother is so easy to go back and forth, kind of like here, where you have 2 things you have to hold in mind at the same time. How you get it, which is kind of complicated, and then what does it mean? And you got to kind of hold 2 very different things in your mind simultaneously. And same thing with talking with my brother about my dad. It was so easy to rotate to here's the hero and here's the goat. And you're just going back and forth between the 2. And it took, integration, and it took time to realize, hey, he was both simultaneously. He was, in one way, a great person, in another way, really horrible to live with. The same kind of skills we might wind up over in here having to develop. All right, now let's look at a problem, and I'm going to switch over to using the board, whiteboard. So let me set up for a moment. Camera. So number 2, let's look at this example. F of x is equal to x squared. Using the second definition, using f prime of a is equal to the limit as h approaches 0, f of a plus h minus f of a over h. Find f prime of 1. Alright, now before I do this, let me show you the magnitude of what we are about to do. If I look at this function, y equals f, or f of x equals x squared, it's a parabola. When its input is 1, its output is 1. And And what we are trying to find is the exact slope of the tangent line right here. Now, folks had said this was impossible to find because if you're 1/1,000,000th of a unit away from 1, it's a different slope. If you're 1/1000,000,000th of a unit away, it's a different slope. There's no way in hell you're going to find the exact slope at exactly this point. Well, Newton and Leibniz found a way to do it, but they had to use this limit idea to do it. Okay, so that's what we're going to get. And from just looking at it, what does that slope look like? Is that bigger than a 45-degree angle line? Because that would be a slope of 1. If it was, yeah, it does. It looks like maybe it's a slope of 2 or 3 or something like this. Maybe. So my estimate, maybe the slope is approximately 3 or something. Now, it could be my picture, because this is a really crude picture. It could be my picture is quite off. So this crude estimate is all I'm looking for. But definitely it's positive, and it looks bigger than 1, more than 45-degree angle. All right. Let's also approximate it in one other way. Let's take the interval 1 to 1.01. The slope of the secant line between 1 and now 1.01 is so close to that I don't want to put it on my graph. But if I do that, now if I made a little table, 1, 1 when you square it, 1.01, when I square that turns out to be 1.0201. So the slope of the secant line is going to be this minus this, the difference in the y's, over the difference in the x's. And then I'm going to get 0.0201 over 0.01. Move the decimal to the right 2 places, top and bottom. 2.01. Ooh. If I do that, I can say, hey, maybe I'm going to update my estimate. I'm going to say, with this information, maybe the slope is going to be 2. Because when I was really close to 1, I got really close to 2. Alright? Now, but these are just estimates. Looking at the graph and using any secant, no matter how close, is not finding the exact answer. To find the exact answer, we have to use algebra. So now we'll find exact. Oh, so example, yeah, find f prime of 1. Find exact answer using algebra. So we're going to use this f prime. We're going to replace the a with 1. So we just rewrite this exact same limit. But every time I see a, I replace it with 1. Alright, before I go on, is everybody convinced that if I can get this limit, I will have this exact answer? Because what it's going to be is, see, this is 1, and then 1 plus h is somewhere over here, and maybe this graph comes up to here, and if I find the slope between these two, I I say the slope of that blue line is a reasonable estimate of the slope of the red line. But then as I make h smaller, it pushes this closer, and then I get an even better estimate. And I say, well, the slope of that blue line is an even better estimate. And if I take the limit of all these slopes, I'll get the exact slope. So, if we're convinced that this is going to give me my exact answer, we can keep going. Close the limit as h approaches 0. Now, I have to resolve f of 1 plus h and f of 1. How do I do that? Anybody have an idea? What do I do?
We're going to do 1 plus h1 squared minus
This is my function, which really means this. F of anything is that thing squared. So I'm going to plug in 1 plus h here and here. And then I'm going to get, now remember we had done this before when we did those difference quotients. Sometimes we did it by writing f of 1 plus h equals and expanding it out and reducing it over on the side and so on. But we can also just leave it in here. 1 plus h squared minus f of 1. 1 goes in each of those. 1 squared over h. And this is an algebraic manipulation of the limit. But if we plug it in right now, h being 0, we're going to get 0 over 0. So its form, remember when we did this? We always write out the form. And the way we had to proceed was use algebraic reduction till we can get rid of that h in the denominator. This becomes, now 1 plus h squared is 1 plus h times 1 plus h. And when you FOIL that out, you get 1 plus, you're going to get an h and another h. The two middle terms make 2h plus h squared, and then minus 1 all over h. And then we see that the 1's cancel, which is equal to the limit as h approaches 0 of 2h plus h squared over h. Now, what I'd like to do is cancel out this h with this h, but I can't. That would be very similar to saying 8 plus 3 over 3 and tried to cancel out the 3's. 11 over 3 does not equal 8, which is what you'd get if you tried to knock out those 3's or something. You can't. But if you had 8 times 3 over 3, you could cancel them out. So we have to turn this from an addition problem into a multiplication problem. But that's what factoring does. What's common to these two is an h. Now it's multiplication problem. What's in parentheses can always be thought of as one letter. And so now, instead of being one of these where you can't cancel, it's one of these where I can cancel. And then I am going to reduce. At this point, if I substitute 0, I'm getting 0 over 0. But as soon as I reduce, I can now substitute the h being 0, and I'm not going to get 0 over 0. This h, as h goes to 0, it drives this thing to 0, and I get 2. And let's compare that exact answer to my estimate. My original estimate was 3. I updated it after doing a secant line with a really close interval. And then when I did it exact, it came to exactly 2. Now, historically, this was incredible. Something that the naysayers had said would never ever be done. You can't ever get the exact slope at 1. 1 billionth of a unit later, it's going to be different. Doesn't matter. this is the exact slope of the tangent line when x is equal to 1, and we got it. Any questions? All right, let me take a snapshot of this and put it in there. Oh no, I got my arm. Let's do the snapshot again. And camera. Let's do another one. So notice f of x equals x squared. We found the instantaneous slope when x is equal to 1. Now let's just modify this problem. Let's make it number 3. We're going to do f of x equals x squared again. We're going to use the same expression for the definition 2 for the slope, but we are going to ask for something different. We're going to find find the slope of the tangent line at x equals, we already did it for x equal 1. Let's do it for x equals 2. Then for x equal 3, x equal 4, 5, 6, 7. Now, what we've just given ourselves the task of is something incredibly repetitive. We're going to have to repeat this thing a whole bunch of times using the same kind of strategy over and over and over again. We need the slope at a whole bunch of points along f of x equals x squared. Now, the long way to do it would be just repeat this whole process again. Just use 2. Actually, instead of x equals, I'm using this notation, at a equals 2, so on. Alright, so I could do it again with 2, and then 3, and so on, but I don't need to do it with a whole bunch of different limits. I can do it in a general way at a. Before I do it at a, though, let's find f prime 2. Let's do it one more time with just a regular number. And then we're going to generalize it to f prime at any value a, and then we're going to get an answer that involves a, and then we'll be able to quickly fill in all of these values. So to do f prime at 2, we rewrite this expression, and then every time you see the a, put 2, and then expand it out. And what I want you to do is try to stay ahead of me. I'm going to give you about 1 minute to get ahead of me, and see if you can stay ahead of me the whole time. If you can't, that's fine. I'll be catching up, but see how far you can stand. Okay, I'm going to start working. I write this exact same expression. Every time I see the A, I just put 2. I use this rule. When I FOIL that out, I get 2 middle terms. 2H and 2H make 4H. The form is 0 over 0 until I do this. Once I cancel them out, then it's not 0 over 0, and this thing will drive to 0. And I get 4. But boy, this is going to take me a long time. I got to do it again with 3, again with 4, again with 5. But no, I don't. Let's do it again. Instead of finding f prime of a single value, let's use the letter A. Now my answer is going to involve A in it. But then we can use that answer as a shortcut to get all these other things. So, f prime at A, I do this, but every time I see the A, I substitute A. Well, I get exactly the same thing. And this algebraic skill, we learned how to manipulate these things, starting with the difference quotient and then going up to limits, was really a powerful tool that we used. And f of A plus H, now A plus H goes here and here, and I just get that, and then A squared over H. When I do this, I FOIL that out, I get A squared. The 2 middle terms are AH plus another AH plus 2AH plus H squared minus A squared over H. This is why you spent so much time learning algebraic skills. You know, since early in your life, it seemed like over and over you did algebra, algebra, algebra. We need it to be so reflexive that you work with letters the same way they work with numbers. And then there's an H common to both of those. And then the h's reduce. And now, as h goes to 0, it has no effect on the 2a term, but it sends that one to 0. And you get 2a. Thus, f prime at any value a, the derivative at any point a, is always equal to 2 times a. Can we now find, yes,
I was just going to say this is specifically for the function x squared.
that's right. It's only for the function x squared. Doesn't have effect, it doesn't have that value for any other function. But for the function x squared, f prime at any point is twice the point, the x coordinate of the point. So f prime at 3, what's that got to be? Well, just double the 3. You get 6. F prime at 4. Double the x coordinate, it's 8. F prime at 5 is 10. Prime at 6 is 12. F prime at 7 is 14. That is incredible stuff. We not only can find out the exact slope at a specific point, we can find it for all points. And let me print screen here and put this into the notes. All right, now, what this also means, let's look at it graphically. There are points in math where I step back and I go, wow. And this is one of those points. If we have the function y equals x squared, all right. What's the slope right here? Can anybody tell me that? What's the slope of that red line I just drew?
-6.
That is correct. All you do is you double the x coordinate and you get that. What's the slope of this one? Not as much. It's only -4. The slope of this one, it's only -2. What's the slope here? It's double 0 and you get 0, but that makes total sense. You're getting a horizontal line. Double the slope of 1, you get 2. Slope of 4. Slope of 6. So we know the slopes everywhere along this curve. And later on you'll learn to appreciate how significant that is. Getting the instantaneous slopes, the slope of the tangent line. That's the essence of the relationship between the input variable and the output variable, is in the instantaneous slope. And we can get it not just at one point, but everywhere, is the power of algebra. All right. Next, so Let's pick one of these points. F of x is equal to x squared. So this, I think the last one we did was number 3, so this will be number 4. F of x was x squared. F prime at 4, we already determined. F prime at 4, all you do is double that input. Only works for this function, but you get 8. Now I'm going to ask a different question. Find the equation of the tangent line. At x equal 4 for the function f of x equals x squared. Alright. So this time, I didn't ask just what's the slope when x is 4. I asked what's the equation of the tangent line at x equal 4. So what I'm asking for is if we go over here to 4, straight up to here, we know this has a slope of 8. But how do you find the equation of that red line? What two pieces of information would be helpful to find
The limit.
the slope of, to find the equation of the line?
You would use y minus f of a equals the slope of sec
Okay,
x minus a.
all right, very good. So to find the equation of a line, we're going to need two things. We need a point and a slope. And then if we have a point and a slope, you can plug it into the point-slope formula. Y minus y1 equals mx minus x1. But we need the point and we need the slope. What's the point? Well, it's x equal 4, so it's 4 comma, and then you substitute 4 into the function. You square 4, you get 16. To get the slope, the only way to get the slope, the instantaneous slope at x equal 4, as Kylie said, was we need the limit. But we've already done that. When we did the limit, in general, we found it was double whatever that number was, so it's 8. So the slope of the tangent line is equal to 8. So we have both of those pieces of information now. We need a point and a slope. We plug them into the point-slope formula. So y minus 16 is 8x minus 4. Y minus 16 is 8x minus 32. Add 16. We get y equals 8x minus 16. Okay. Now, when you get the equation of a tangent line, and you have the function, what's kind of interesting to do is to graph both of these on the same coordinate grid. So that's what I'm going to do here. I'm going to go to Wolfram alpha. Let's y equals x squared and y equals 8x minus 16. Let's see if it'll graph both of them on the same axis. It does. And when it does, what do we notice? That we get a tangent line at x equals 4. Right above x equals 4, that's where we nick the curve. And it just nicks it. That's the equation of the tangent line. Here's the y equals x squared, the blue curve is y equals x squared. And we get it, and it'll always, if you did it right, and then you graph both the original and the equation of the tangent line, it'll just nick the curve at that x value. Again, really powerful stuff that we have, and we can confirm our answers by graphing them like this. Any questions or comments? All right. Let me print screen. And let's come back to the camera. Now, there are some problems that are going to get a little messy and a little bit tricky. Just like some of those limit problems got a little messy and tricky that we had done earlier. Before we do that though, let's just review. Definition f prime at a equals. I want you to write out the rest of this. See if you can remember. I'm going to start it out for you. The limit, and we'll use the second definition. As h approaches 0, what goes in the top and what goes in the bottom? Don't look it up. See if you can remember it. Test your memory. We're going to wind up memorizing this. So it's good to start now. All right, anybody need more time? All right, so I can remember that h was in the bottom. But what was the h representing? Remember, that was the change in the x. It was really a plus h minus a. And the a's had canceled out and you got the h. The top was the difference in the y's. F of a plus h minus f of a, like this. Okay, so that's important to start putting that into memory. This definition of the derivative as this limit, and it's a difference quotient. Let's take this problem. F of x is equal to the square root of x. Find the equation of the tangent line at x equals 4. So what problem are we at now? Is this like problem number 4 or something like this? Maybe 5?
We're at 5.
5, thank you. All right, a rough estimate of this. F of x equals x squared, I know, is the upper half of a sideways parabola. And when x is 4, the y is only going to be 2. And when I find that slope, the instantaneous slope that's just going to nick the curve there, I'm going to get something less than a 45-degree angle. I'm going to get m equals some fraction. I don't know, 1/5 or something like this. Rise 1, run 5. This is my estimate. Now, I could refine my estimate by going interval 4, 4.001, something like this, but I don't have enough time to do that. Let's just go right into the exact slope. Now, if I find the equation of the tangent line, to find the equation of that blue line at x equals 4, I'm going to need a point. That part is easy. 4, comma, plug it in, 2. I'm going to need a slope. Well, I don't know what the slope is. But the slope is going to be f prime of 4. So whatever we find for f prime of 4 is going to go right there. F prime of 4 is, we use this definition, and by the way, to memorize this really quickly and efficiently is every time you need to use it, make yourself write out this from memory first and then check to see that you wrote it out correctly. If you just look it up every time you need it, because like in all the homework problems, you're going to need this little definition. Either this one or the definition number 1. And when you force yourself to write it out from memory, you'll find that you'll have it memorized real quick. And when you force yourself to write it from memory and make you get it wrong, you tend to find out, oh, that's the part I don't tend to remember, and it really helps you remember that part especially good the next time. So this is equal to the limit as h approaches 0 of f. Every time I see a, replace it with 4. Now I'm expecting to get an answer kind of small when I finish, but let's see. Now the function is square root. So I just plug in 4 plus h into the square root function. I plug in 4 into the square root function. Now this 4, when you square root it, turns out to be 2. Alright, now, when I substitute 0 in for the h, I'm going to get my form. I'm going to get 0, because 2 minus 2 is 0 over 0. It's the indeterminate form. So, I'm going to have to do some algebraic manipulation. I'm going to multiply top and bottom. The same trick that we've done before. What's the fancy name?
Conjugate.
Very good. Same two terms, but change the sign. Alright, and then equals, h approaches 0. Now when I multiply that out, this times this, the square roots just go away. The two middle terms are going to cancel each other out. And then the last term is minus 4. And then on the bottom, I'm not going to multiply that out, because that h is what I want to cancel out. Okay, now I notice these two kill each other off, and also this and this kill each other off. So if you are struggling with these kind of ones with the square roots, you're going to get more practice at this kind of stuff. And all I'm left with in the numerator is h. Now, the form is still 0 over 0 until I reduce. And once I reduce, now I can send this h to 0, and I will get 1 over square root of 4 plus 2, which is 1 over 2 plus 2, which is 1/4. So, what did I estimate? 1/5. But what did I actually get? 1/4. Pretty good. So, this, we come back over to here. We put in 1/4. So now I have, let me take a picture. We come back over here, and I'm going to need some space, so let me erase from here on down. So I have a point and a slope. The equation of the tangent line is going to come from the point slope formula. Y minus y1 is mx minus x1. Y minus 2 is equal to m 1/4 x minus the x1, which is 4. And then I get y minus 2, 1/4 x, distribute the 1/4, minus 1, add 2, y equals 1/4 x plus 1. That is my final answer. It asks me, find the equation of the tangent line when x is equal to 4. Now, look at this blue line up here. Does it look like it has a slope of 1/4? Rises 1, run 4. Does it look like its y-intercept is going to be 1? Yeah, well, send it back, it could be there. But I'm going to use Wolfram alpha to really check this out. So let's go here. Let's put in y equals, now in Wolfram alpha you can do SQ, you see as soon as you start this it tells you all these things. RT is how you do square root of x. Y equals square root of x, comma, y equals 1/4 x, which is the same as x divided by 4, plus 1. So I'm going to hit enter. And it's happening just like before. Right at 4, directly above it, we nick the curve right there. That's the tangent line. And we found the equation of the tangent line right here at x equals 4. Any questions or comments?
If you were to, out of curiosity, if you were to, for these different equations, graph the derivative function,
Mm-hmm.
would be basically looking at a graph that is charting the journey of the slope along the function, basically.
Very good anticipation. That's what's going to happen very soon. We're going to be getting into the derivative as a function itself. And then we'll have two graphs. One is the graph of the original function, and the other one is the graph of the slopes. And we'll put them on the same XY grid. And that's what we're going to be doing very soon. In fact, that might be in the very next section. I think it is. I think we're going to get at in the 3.2. So, great anticipation. Any other comments, questions? All right, so the homework is 3.1. That'll be spot checked tomorrow, which is on Wednesday. And that is also due to be, you have your final form in by Thursday. What we're going to do tomorrow is 3.2, but I won't spot check 3.2 on Thursdays because we have an exam on Thursday. So if you want to just save the 3.2 homework for over the weekend, you can do that. We'll cover 3.2 tomorrow. I'll assign it tomorrow, but the spot check won't be until Monday of the following week. So you can devote your time to the getting ready for the test. All right, we'll stop at this point, and I'll see you all tomorrow. Oh, I got to stop the video, and you're welcome. You guys are great at reminding me about the video. I really appreciate that.